A single, mysterious whisper, the wow signal, captured in 1977 by a radio telescope in Ohio, still stirs curiosity and wonder in the minds of scientists and dreamers alike. For just 72 seconds, a faint but strong radio transmission blazed from the depths of space, aligning perfectly with the kind of frequency scientists imagined an intelligent civilization might use to announce itself. When Jerry Ehrman, the astronomer scanning through the data, circled it in red pen and wrote the word wow, he unknowingly etched a phrase that would echo through decades of cosmic mystery. What makes the wow signal so haunting is not only its strength but its silence afterward. For those 72 seconds, it was as if someone, somewhere, spoke across the unfathomable void of the cosmos and then retreated into absolute stillness. Despite many attempts, the signal never returned, no repetition, no second whisper. It was like a fleeting dream that fades as soon as one awakens, leaving behind only the lingering memory of something extraordinary that can never be fully recalled or proven. The source of the signal appeared to come from the constellation Sagittarius, near a group of stars that hides within the Great Galactic Center. That location, already shrouded in mystery and cosmic dust, seemed a poetic place for such a whisper to appear. Yet the signal carried no clear code, no decipherable message. It was pure frequency, a steady and sharp tone, almost too perfect to be a natural phenomenon, but too brief to be a deliberate communication. It sits in the middle ground between nature and intent. Scientists debated countless theories to explain it. Could it have been a passing comet, reflecting radiation at just the right angle? Could it have been interference from Earth, disguised as something alien? Or perhaps it was a cosmic phenomenon we still do not understand, a natural beacon that happened to align with the exact range we associate with interstellar contact. Each theory brings its comfort, but none fully explains why this signal came once and never returned. It remains ungraspable, like smoke in the night. There is also something deeply human in the way we cling to the wow signal. We look at the stars with both science and longing, searching not only for evidence but for companionship in the dark. The signal became more than a scientific curiosity, it became a symbol, a reminder that perhaps we are not alone. And even though rational explanations exist, they do not extinguish the gentle hope that maybe, just maybe, someone out there sent us a greeting across the ocean of stars. Jerry Ehrman himself, though careful and scientific, admitted to feeling a spark of wonder when he first saw the printout. His red-inked exclamation was not cold data but a burst of awe, a human reaction to something that seemed beyond calculation. Decades later, the handwritten wow still feels like a personal note from history, a glimpse into the exact moment a scientist touched the edges of the unknown and could only answer with one small, astonished word. Attempts to rediscover the signal have been many. Large telescopes have scanned that same patch of sky, night after night, year after year, waiting for the whisper to return. But the silence remains constant, as though the universe itself teased us with a fleeting brush of contact and then turned away. This silence is almost louder than the signal itself. It makes the original event seem more fragile, more precious, as though it existed in a single, unrepeatable moment in time. Some believe the signal was extraterrestrial, a deliberate attempt at communication that we simply did not understand. After all, if intelligent life exists, what better way to test the waters than with a simple broadcast, brief and strong, then withdrawn? It would be like tossing a stone into a vast lake and watching the ripples, waiting to see if anyone notices. But if that were true, why did it never happen again? The question lingers, unanswered, heavy with possibility. Others find comfort in the idea that it was merely natural. That the universe is filled with strange signals, echoes, and flares, and the wow signal was nothing more than an unusual but explainable occurrence. But even those who lean toward this explanation admit the mystery is unsolved. The comet theory, once proposed, falls apart under scrutiny. The possibility of human interference does not perfectly align. Each explanation fails to close the door entirely, leaving it ajar for wonder to seep through. Imagine for a moment that it truly was a message. Not words, not sentences, but a simple hello written in the language of frequencies. The brevity could have been intentional, like the first knock on a door before deciding whether to knock again. Perhaps the sender did not wish to overwhelm us, or perhaps they too were unsure if anyone was listening. The beauty of the thought lies not in proof but in possibility, in imagining a hand reaching across light years to tap on the window of our world. The wow signal lives in the space between certainty and mystery. It cannot be dismissed outright, but it also cannot be confirmed. And in that in-between space, our imagination thrives. It is the pause in a song, the silence after a whisper, the half-remembered dream that keeps us awake at night, wondering. The human mind is drawn to such gaps, to mysteries that cannot be resolved, because they allow us to weave stories of our own, filling the silence with meaning. Over time, the story of the wow signal has grown into something larger than science. It appears in books, documentaries, and countless conversations about alien life. People who have never studied astronomy know of it and feel its weight. It has become part of our cultural memory, our shared myth, a reminder that science and wonder often walk hand in hand, and that sometimes the smallest event, a blip in data, a faint tone, can ripple across generations. The numbers themselves are cold, yet elegant. The signal was recorded at the 1420 MHz frequency, the exact emission frequency of hydrogen, the most common element in the universe. Scientists often argue that if an intelligent civilization wished to communicate, they would use hydrogen's frequency as a universal marker. That the wow signal appeared precisely there is what makes it so chilling, so strangely precise. It was as if the message was hiding in plain sight, waiting to be noticed. And yet, it never returned. Not once. This absence gives the wow signal its dreamlike quality. In dreams, people appear and vanish, words are spoken and then forgotten, and the logic of the moment fades upon waking. The wow signal feels like one of those fleeting encounters, a message that brushed against us while we slept beneath the stars, only to dissolve as soon as we opened our eyes. We are left chasing its shadow, unable to grasp its form. There is something almost poetic about its loneliness. A single signal, standing alone in the vast ocean of silence. The universe is billions of years old, stars are countless, and galaxies stretch beyond measure. In all that immensity, we caught one whisper, one fleeting note, like hearing a single violin in a desert of silence. It makes us feel both smaller and larger at once, tiny in the face of infinity, but significant enough to have perhaps been noticed. The wow signal has become a kind of campfire story for scientists. When young astronomers gather, they still whisper about it, their voices tinged with both skepticism and wonder. For many, it was the spark that drew them into astronomy in the first place, the possibility that one night, when the telescope is pointed just right, another whisper might emerge. It is not only data, it is a promise, a challenge, an invitation to keep listening. Even skeptics cannot deny the beauty of it. The sheer chance of the event, the precision of its frequency, and the haunting silence that followed make it a perfect mystery. It is a reminder that science is not only about answers but about questions. The wow signal did not solve anything, but it deepened our curiosity, urging us to keep asking, to keep reaching, to keep wondering about the unseen worlds that might be speaking in ways we cannot yet understand. For some, the wow signal is not a mystery to be solved but a gift to be cherished. It is a reminder that the universe still holds secrets, that not everything can be explained or catalogued. In an age when we map galaxies, photograph black holes, and measure the faint afterglow of the Big Bang, the wow signal stands as a gentle protest against certainty. It tells us that some corners of reality remain dimly lit, and perhaps they should remain so, to keep wonder alive. Imagine sitting alone beneath a night sky, the stars scattered like quiet lanterns across the dark. Now imagine that, for just over a minute, one of those lanterns whispers your name, then falls silent again. That is the feeling of the wow signal, an intimate brush with the infinite, as though the cosmos itself leaned close for a heartbeat before withdrawing, leaving you forever wondering what it meant. It is less about science and more about the delicate ache of curiosity. Decades have passed since 1977, yet the signal has not faded from memory. If anything, time has made it stronger, more legendary. Its very lack of closure keeps it alive. A solved mystery fades into history, but an unsolved one grows, like a vine, wrapping itself around our imagination, our art, our longing. The wow signal endures not because of what it explained, but because of what it refused to explain. It left a silence that speaks louder than sound. And so the story continues, unresolved and unending. The wow signal is no longer just about radio astronomy. It is about the human heart, about our need to listen and to be heard. It is about our desire to reach beyond ourselves, to stretch across the gulf of stars and touch the unknown. Whether it was alien, natural, or a trick of chance almost no longer matters. What matters is that, for a single minute in 1977, the universe whispered, and we listened, and we are still listening even now. Visitors from another star, interstellar wanderers, the name itself feels like something out of a timeless tale, and yet it is real. In 2017, astronomers first spotted such a traveler drifting through our solar system, an object unlike anything seen before. They named it Oumuamua, a Hawaiian word meaning a scout or a messenger from afar. 4 weeks, telescopes followed its unusual path, watching as it swept past the sun on a journey that began far, far beyond our familiar system of planets and moons. Unlike comets and asteroids we know, this visitor's trajectory could not be explained by normal solar system origins. Its speed was too high, its approach too strange. It did not circle the sun like a planet, nor did it settle into orbit like a captured comet. Instead, it came in fast, swung around our star, and then left just as quickly, never to return. Its path was hyperbolic, meaning it would travel outward into the galaxy forever. This confirmed the astonishing truth: it came from another star. Oumuamua's shape and behavior made it even more mysterious. Some measurements suggested it was long and thin, like a giant cigar or a shard of rock, tumbling as it moved. Others hinted at a flatter, pancake-like form, unlike anything we had seen among the rocks of our own solar neighborhood. And as it passed by, astronomers noticed a subtle acceleration, as though something beyond gravity was gently pushing it forward. The cause was debated, and mystery clung to it like a veil. For a moment, whispers of alien technology filled the air. Could it have been a spacecraft, perhaps abandoned, or perhaps still functioning in some unknown way? The idea thrilled some, unsettled others. But the majority leaned toward natural explanations, perhaps gases escaping from its surface, like a comet venting as it warmed near the sun, even though no comet-like tail could be seen. Each explanation raised more questions than answers, deepening the mystery rather than solving it. Oumuamua was not alone in changing how we see the universe. Only 2 years later, in 2019, another interstellar visitor was detected, Borisov, a comet that undeniably came from beyond our star. Unlike Oumuamua, Borisov looked more familiar, with a long tail of gas and dust trailing behind it, proof of its icy heart. This confirmed that interstellar wanderers are not rare curiosities but part of the greater story of the galaxy, drifting fragments from other solar nurseries, carrying whispers of distant suns. These travelers remind us that the stars are not separate, sealed realms, but part of a grand, interconnected sea. Just as waves carry driftwood from one shore to another, gravity and time send rocks, ice, and fragments from one system into the next. Some of them wander for millions of years before crossing paths with another star, their journeys silent and unrecorded until they briefly pass before curious eyes like ours. Each is a story written in stone, carrying the memory of another sun. The presence of such wanderers stirs deep thoughts about cosmic exchange. Perhaps they carry chemical ingredients, organics, or even frozen water that once belonged to distant worlds. In this way, life's building blocks might travel across stars, hitchhiking through the galaxy on these silent couriers. This idea, called panspermia, suggests that the seeds of life could be spread like dust in the wind, reaching fertile ground when conditions are right, planting the possibility of life far beyond where it first began. Oumuamua's name fits it perfectly, a messenger. Though silent, though shapeless in our telescopes, it felt like a note slipped under our door by the cosmos itself, saying, "You are not alone. Other worlds exist, other stories unfold." The thought of holding a fragment of another star in our gaze, even for a short while, filled hearts with wonder. It was as if the universe reached out to remind us of its vastness and its habit of surprises, just when we begin to feel familiar with it. When astronomers first announced Oumuamua, it sounded like fiction stepping into reality. A true interstellar object, right here, in our solar system, visible to us before slipping away forever. The feeling was bittersweet. We could study it for a brief moment, but never capture it, never send a spacecraft in time to chase it. It was a passing guest at our cosmic doorstep, staying only long enough to leave us with questions and wonder. Then it vanished into the eternal night. The strange acceleration of Oumuamua remains one of its greatest puzzles. If it was a comet, why no visible tail? If it was only rock, why did it speed up as though some invisible hand pushed it? Some scientists suggested it might have been covered with hydrogen ice, sublimating invisibly. Others imagined exotic compositions, like nitrogen ice from the surface of a shattered exoplanet. Every idea was fascinating, every attempt at explanation adding another layer to its enigmatic presence. Borisov, in contrast, gave us comfort through familiarity. A comet from another system, looking almost like those we know, only slightly different in its makeup. It was icy, dusty, and glowed as it warmed near the sun, a traveler shaped by a different star's cradle but still recognizable. Together, Oumuamua and Borisov painted a balanced picture, one strange, one familiar. One a mystery that refuses to be solved, the other a reassurance that the universe shares more with us than we might think. These visitors show us the galaxy is not closed off or isolated. Material drifts from one solar system to another, blurring the boundaries of what belongs where. Our Earth itself may hold atoms, molecules, even dust grains that began around other stars long ago. In a way, we too are made of wanderers, our very bodies carrying the legacy of cosmic migration. When we look at Oumuamua or Borisov, we are seeing a mirror of our own past, a reminder of the shared materials that weave galaxies together. There is something tender about their brief stays. They do not linger long, nor do they ask for attention. They pass through silently, like birds crossing the night sky, noticed only if one happens to be watching. And yet, the little time we do spend with them leaves lasting imprints, shaping our questions, inspiring our science, and feeding our imagination. Their transience makes them beautiful treasures that can never be kept, only remembered and wondered about. Imagine if, long ago, a fragment like Oumuamua had landed on Earth instead of simply passing by. What secrets would it have carried within its stone or ice? Could we have touched, with our own hands, a piece of another star's story? That longing still lingers, a quiet ache within astronomers who dream of one day catching such an object before it leaves, perhaps sending a mission to study it up close, to peel back its silence and let it speak in the language of minerals and molecules. Future telescopes are being designed with these very visitors in mind. We now know they exist, and so we prepare to find more. Surveys will scan the sky, not just for nearby asteroids but for the faint signs of wanderers on hyperbolic paths. Perhaps next time, when one approaches, we will be ready. Perhaps we will launch a probe to intercept it, to ride alongside it, and to listen as it carries stories of another star's creation, written across its frozen skin. The arrival of interstellar visitors also changes how we think about the galaxy as a whole. No longer do we see solar systems as isolated bubbles, but as open shores where currents of gravity carry debris from one to another. The galaxy becomes like an ocean, its stars like islands, and the wanderers like bottles drifting on the tide, each containing unknown messages from unknown places. We may never open some of these bottles, but even seeing them reminds us of the greater ocean we live in. The mystery of Oumuamua still lingers in scientific papers, debates, and imaginations. Was it natural? Was it artificial? Was it something entirely beyond our current understanding? The truth may never be known, and perhaps that is the beauty of it. It forces us to admit that not everything can be neatly explained. It reminds us that the universe still has room for wonder, still has the power to surprise, still has secrets that resist even our brightest minds. Borisov, by contrast, offers comfort in familiarity, yet it too was astonishing. To look at it was to gaze at the breath of another star, to see ice and dust that never belonged to our sun but instead carried the fingerprint of another system's chemistry. To sample such material would be like tasting the waters of a distant shore, proof that our galaxy is not just vast but interconnected in ways we are only beginning to understand. These interstellar wanderers may also shape worlds in ways we cannot yet imagine. If they carry organics or water, and if they strike young planets, they could sow the seeds of life itself. Perhaps our Earth owes some part of its life-giving richness to a visitor long forgotten, a fragment from another star that quietly delivered the spark we needed. The thought humbles us and connects us to a wider story, one that spans light years and billions of years, one that is still unfolding. They are reminders that we are not only Earthlings or children of the sun but citizens of the galaxy. The materials that shape us, the molecules that compose us, are not bound by the limits of a single star. They drift, they wander, they mix and mingle across vast distances. Oumuamua and Borisov are simply the visible face of this truth, fleeting messengers that reveal what has always been happening, the endless sharing of matter across the cosmic sea. And so, visitors from another star leave us with both wonder and longing. We wonder at their mystery, their beauty, their strangeness. We long to touch them, to know them, to hear the full story they carry across the gulfs of time and space. Though they pass quickly, they change us, reminding us that the universe is alive with journeys unseen, and that we too are wanderers, listening for whispers from beyond, waiting for the next messenger to appear against the backdrop of the stars. Tiny flashes, enormous mystery, fast radio bursts. They are among the strangest and most captivating signals ever heard by human ears stretched toward the cosmos. Imagine, in the silence of the universe, a sudden crackle, a powerful burst of radio energy lasting only a fraction of a second, yet releasing more energy in that heartbeat of time than the sun emits in days. They are brief, unpredictable, and impossibly distant, arriving to us from galaxies far, far away, like cosmic lightning bolts striking across the dark sea of space. The first of these bursts was discovered almost by accident in 2007. While combing through old telescope data, scientists found a flash of radio energy so intense and so brief that at first they thought it must be a mistake, an error in the instruments. But it was real. The burst was sharp and clear, its signal stretched by cosmic distance, like a voice echoing across mountains. And in that instant, the universe had revealed a new mystery, one we were entirely unprepared for. Since then, many more fast radio bursts have been found, each one lasting mere milliseconds, yet each one carrying enough power to rattle our sense of scale. They come from galaxies millions, sometimes billions of light-years away. Their signals travel across intergalactic voids, stretched and softened by dust and plasma, yet still arriving at our instruments with astonishing strength. The fact that such tiny bursts can reach us from such unimaginable distances makes them feel like whispers of giants. The origin of these bursts remains hidden. Some believe they come from neutron stars, the collapsed remnants of massive stars, so dense that a teaspoon of their matter would weigh billions of tons. In particular, magnetars, neutron stars with magnetic fields trillions of times stronger than Earth's, are prime suspects. A sudden quake on their surface, a violent rearrangement of magnetic fields, could unleash a flare of energy that escapes as a radio burst. But even this idea does not answer every question. A puzzle deepens when we discover that some bursts repeat. While most are one-time flares, vanishing forever after a single blink, a few have returned again and again from the same patch of sky. These repeating bursts suggest something more stable, more complex, perhaps even cyclical. It is as though a lighthouse stands in the darkness, its beams sweeping across us every so often. But unlike any earthly lighthouse, this one is hidden on a world or within a system beyond imagination. Others theorize that fast radio bursts may come from cataclysmic events, stars colliding, black holes merging, or even the final collapse of a neutron star into a black hole. These one-time bursts could be the dying screams of stars, echoes of destruction traveling across the galaxy. Yet if that were true, how do we explain the repeaters? The universe seems to be playing two songs at once, one of finality and one of persistence, leaving us unable to decide which story is true. Some even whisper of stranger possibilities. Could they be artificial signals, the work of civilizations harnessing unimaginable energies? After all, the bursts are bright, quick, and distinct, like intentional transmissions. A few scientists have speculated about alien starships using beams of radio waves to propel solar sails, their leakage reaching our telescopes across the void. While mainstream astronomy treats such ideas with caution, the mystery of FRBs is deep enough to keep such dreams alive. What makes these bursts both beautiful and haunting is their unpredictability. They appear without warning, like flashes of lightning in a night sky, gone before you can even turn your head. Telescopes must be constantly listening, waiting, hoping to catch one in the act. When one is detected, the thrill is immense, a fleeting signal, a cosmic heartbeat that will never come again in exactly the same way. And then, silence returns, as if the universe closed its eyes once more. Over time, patterns have begun to emerge. Some repeating bursts show regular rhythms, repeating every few days, weeks, or even months. This regularity suggests an orbiting body or a spinning star, something mechanical yet natural. Still, the energy released is staggering, far beyond anything our own sun produces in so short a time. It is like hearing a ticking clock made of lightning, each tick strong enough to be heard across billions of light years. The rhythm comforts us, yet the power unsettles us. The sheer distances involved make FRBs astonishing. If we consider that light itself takes millions of years to cross from their galaxies to us, then every burst we hear is an echo of something that happened long before human beings even existed. To detect them is to listen to ancient moments, the remnants of violence or mystery that unfolded when Earth was still young. Each FRB is a message from the past, reminding us that the universe's stories unfold on scales far beyond our own. Technology has advanced so quickly that we now find hundreds of FRBs, cataloging them like treasures. Telescopes with wide fields of view, like CHIME in Canada, listen constantly, capturing bursts as they ripple through the cosmos. Each detection adds a new line to the grand puzzle. Some bursts cluster in certain galaxies, some scatter randomly across the sky. Each one is unique, like a snowflake, yet together they form a storm we are only beginning to understand. One burst, discovered in 2020, came from much closer to home, within our own galaxy. This was the first time an FRB had been linked directly to a magnetar, confirming that at least some bursts come from these strange stars. The detection was a breakthrough, tying the mystery to a tangible source. Yet even then, questions remained. Why are most FRBs so much brighter than the one we saw nearby? Are there multiple kinds of bursts, or are we seeing only parts of a much larger story? The repeating FRBs, particularly those with complex structures, feel especially enigmatic. Some bursts arrive in clusters, with multiple flashes in rapid succession, like drumbeats instead of single strikes. Others seem to change over time, as though their engines are not steady but evolving. Such patterns make them feel alive, dynamic, hinting at mechanisms still hidden from us. Each burst is like a coded message, its meaning just beyond the reach of our current understanding. The beauty of FRBs lies not only in their science but in their poetry. To imagine a flash of energy so powerful that it crosses entire universes of distance, yet so brief we might miss it in the blink of an eye, is to glimpse the dual nature of reality, fleeting yet eternal, small yet vast. They remind us that the universe is both gentle and violent, both silent and filled with sudden song, each burst a reminder that the cosmos is alive with phenomena beyond imagination. Some scientists dream of using FRBs as tools. Because their signals are stretched and delayed by the matter they pass through, they could serve as probes of the invisible structures between galaxies. By studying them, we might map the intergalactic medium, the faint gases and plasma that fill the spaces between stars and galaxies. In this way, the bursts could become lanterns, lighting up the darkness between cosmic islands, showing us what is otherwise invisible. Others think of them as cosmic beacons. If civilizations wanted to announce themselves, FRBs would be perfect, bright, unmistakable, detectable across unimaginable distances. Of course, this remains only speculation, but the very fact that FRBs invite such thoughts shows how deeply they stir our imagination. They are unlike any other phenomenon, so sudden, so energetic, so unpredictable, that they leave room for the wildest possibilities alongside the most careful science. What makes them soothing to ponder at night is their fleeting nature. They are reminders of how quickly moments pass, how even the grandest explosions can be over in the blink of an eye. Yet the memory of those moments lingers, traveling across time and space until it reaches us, perhaps millions of years later. They are like brief candles lit in distant windows, glimpsed across a dark plain, their flames long extinguished but their light still journeying toward us. Each FRB we detect is unique, but together they hint at a cosmic orchestra, each burst a note in a song we cannot yet hear in full. Some notes are sharp and loud, some soft and repeating, some singular and gone forever. We are at the beginning of learning this music, straining to catch each tone, recording them one by one, hoping that eventually the melody will emerge. Until then, the bursts remain both chaotic and beautiful, fragments of a score written across galaxies. There is comfort in knowing that such mysteries still exist. In a time when we have mapped planets, walked on the moon, and peered into black holes, it feels reassuring that the universe still holds secrets beyond our reach. FRBs are one of those secrets, a reminder that no matter how much we know, there are always sudden bursts of the unknown waiting to surprise us. They keep science alive, they keep curiosity burning, they keep the night sky endlessly compelling. The more we study them, the more we realize how varied they are. Some come as single blinks, some as repeating clusters, some as rhythmic pulses. Some are faint, others blindingly bright. They defy a single explanation, forcing us to accept that the universe does not play by simple rules. Perhaps there are many engines behind them, many stories converging into one phenomenon. This complexity makes them even more fascinating, even more worthy of our patience and wonder. And so, fast radio bursts remain a riddle carved in light and time. Tiny flashes that cross unimaginable distances, enormous mysteries contained in milliseconds of sound. They are whispers from galaxies far away, some never to be heard again, some returning like echoes of a hidden rhythm. Whether they are natural storms or deliberate signals, they remind us that the cosmos is not silent, but alive, filled with sparks that blink and vanish. And as we listen, we drift deeper into the soothing, endless mystery of the stars. The star known as Tabby's star, officially catalogued as KIC 846-2852, first came to public attention when astronomers noticed its unusual dimming pattern in data collected by NASA's Kepler Space Telescope. Most stars that dim do so in regular intervals, typically caused by a planet crossing in front of the star and blocking a predictable portion of its light. But Tabby's star did not follow this neat rhythm. Instead, it dimmed sporadically, sometimes fading by small amounts and other times plunging by up to 22%, a phenomenon never before seen in stellar observations. What makes this dimming particularly mysterious is the sheer irregularity of it. With typical exoplanet transits, astronomers can easily model the dips in brightness based on orbital mechanics. Planets block the same fraction of starlight each time they pass in front, and the event occurs in a strict repeating cycle. But Tabby's star refused to conform. Its dips occurred unpredictably, lasted for varying lengths of time, and sometimes did not recur at all. This chaotic behavior suggested something far stranger than the presence of ordinary planets. At first, astronomers wondered if giant clouds of dust surrounding the star might explain the odd dimming. Dust clouds can scatter and block light, and if they happen to orbit in loose, irregular formations, they could potentially cause the kind of unpredictable dimming events observed. Yet when researchers analyzed the star's light in multiple wavelengths, they discovered that the dimming was not always consistent with dust behavior. Some dips blocked blue light more than red, as dust typically does, but others reduced all colors equally, hinting at a different kind of obstruction. This discrepancy opened the door to a wave of speculation, not just among astronomers but across the broader public. Some even suggested the possibility of alien megastructures, like Dyson swarms, giant collections of energy-harvesting panels built by an advanced civilization around their host star. While most scientists did not consider this a likely explanation, the sheer strangeness of the dimming left room for such theories to enter popular imagination. The idea that Tabby's star might be surrounded by massive artificial structures captured media attention and sparked discussions far beyond academic circles. More grounded scientific theories also took shape. One possibility was that Tabby's star was surrounded by the remnants of a shattered planet or comet swarm. A catastrophic breakup event could release large amounts of debris, forming clumps that sporadically drifted in front of the star and caused varying dimming depths. Cometary fragments in particular could explain irregularities, as their tails and loose formations would not produce uniform light curves. However, the sheer scale of the dimming required an enormous number of comets, far beyond what would typically be expected. Adding to the puzzle, astronomers noticed that the star wasn't just experiencing short-term dips. Long-term observations indicated that Tabby's star was gradually dimming over decades, at rates far higher than expected for a stable main-sequence star. This slow-fading trend, combined with sudden sharp dips, painted a picture of a star undergoing processes not easily explained by conventional astrophysics. It suggested that whatever mechanism was at play operated on both short and long timescales. The star itself is an F-type main-sequence star, slightly larger and hotter than our Sun, and located about 1,470 light-years away in the constellation Cygnus. On the surface, it should behave like countless other stars of similar type, radiating steadily with only minor variations. Yet its behavior has proven exceptional. That such an ordinary-seeming star could host such extraordinary light fluctuations makes it all the more mysterious, pushing astronomers to test the limits of their understanding of stellar environments. To probe the mystery, researchers launched ground-based follow-up campaigns using observatories worldwide. Spectroscopic studies sought to determine whether the dimming was wavelength-dependent, which would support dust-related theories. Some results did lean toward dust, as certain dips blocked more short-wavelength light. Yet not all data aligned, leaving ambiguity unresolved. The star stubbornly resisted any single, satisfying explanation, which kept the scientific debate alive. In 2016, the mystery deepened further when the star dimmed significantly in real time, allowing astronomers to study it as the event unfolded. Telescopes across the globe focused on Tabby's star, measuring its behavior in multiple wavelengths simultaneously. While some findings supported dust as the culprit, inconsistencies remained. If dust were solely responsible, it should have left clearer spectral signatures, but the results were mixed. Once again, Tabby's star played the role of a cosmic enigma. Some astronomers proposed that intrinsic stellar processes might explain the dimming. Perhaps the star itself was experiencing unusual magnetic activity or internal oscillations that altered its brightness in erratic ways. However, models of stellar physics offered little support for such mechanisms at the magnitude observed. Stars can indeed fluctuate due to pulsations or starspots, but these phenomena usually follow recognizable cycles, unlike the wild irregularity seen here. This made intrinsic variability an unlikely candidate. Another intriguing idea was that Tabby's star might have swallowed a planet or other large body in its past, creating a lingering cloud of debris orbiting chaotically. Such an event could produce both long-term dimming as dust disperses and shorter, sharper dips as clumps pass by. The aftermath of such a cosmic feast could persist for centuries, meaning astronomers might be witnessing the stellar environment slowly digesting the remains of a devoured world. Though speculative, this hypothesis fits some aspects of the data. Citizen scientists played a vital role in bringing the star's mystery to light. The Planet Hunters project, which allowed volunteers to sift through Kepler's data, first highlighted the unusual dimming pattern. This collaboration between professional astronomers and dedicated amateurs underscored how unexpected discoveries can emerge from collective human curiosity. Without these watchful eyes, Tabby's star might have slipped by unnoticed, buried within the mountain of data collected by space telescopes. Tabby Boyajian, the astronomer after whom the star was nicknamed, led extensive campaigns to monitor its behavior. She and her team coordinated observations during active dimming events, engaging both professionals and enthusiasts worldwide. This collective effort not only advanced the science but also demonstrated the power of community-driven astronomy. The star became a kind of shared puzzle, inviting contributions from across the globe in pursuit of understanding. Over time, the weight of evidence leaned increasingly toward dust as the leading explanation. Multi-wavelength observations showed patterns consistent with fine dust grains scattering light, especially during smaller dimming events. However, the mystery did not fully evaporate. Dust could explain much, but not everything, particularly the long-term fading trend. Astronomers began to refine models of circumstellar dust behavior, exploring whether large, asymmetric disks or clouds could account for both short-term dips and long-term dimming. The alien megastructure theory, while exciting, gradually lost traction among scientists as dust-based explanations grew stronger. Nevertheless, it played an important role in keeping the mystery in the public eye. Speculative ideas often capture imaginations in ways that pure technical explanations do not, and in this case, it brought widespread attention to a star that might otherwise have remained an obscure data point. It also highlighted how the search for extraterrestrial intelligence intertwines with mainstream astrophysics. From a broader perspective, Tabby's star teaches an important lesson: the universe remains full of surprises. Despite centuries of studying stars, astronomers continue to encounter phenomena that defy existing models. Each anomaly forces scientists to rethink assumptions and refine theories, pushing knowledge forward. Tabby's star serves as a reminder that the cosmos is not a solved puzzle but a vast, dynamic mystery where even familiar objects can behave in ways no one expects. Future telescopes may help settle the debate. Instruments like the James Webb Space Telescope and next-generation ground-based observatories are capable of probing dust properties with unprecedented precision. By observing Tabby's star across broader spectra and with higher resolution, astronomers hope to determine exactly what materials are responsible for the dimming and how they are distributed around the star. Such studies may finally unravel the decades-old enigma. If the dust theory proves correct, Tabby's star may serve as a case study in stellar environments rich with circumstellar material. It could represent a star caught in a unique stage of evolution, or one surrounded by unusual planetary debris. Understanding it better could shed light not just on this one star, but on the variety of environments other stars may host. This has implications for planetary system formation and destruction, offering clues to cosmic processes that shape worlds. Another intriguing angle lies in the connection to long-term stellar variability. The gradual fading of Tabby's star might reveal mechanisms that operate on timescales not usually observed by humans. With modern technology, astronomers can compare data across centuries, using historical photographic plates alongside current observations. This extended timeline shows patterns that would otherwise remain hidden, hinting at slow cosmic changes that unfold over human lifetimes. While Tabby's star may eventually be explained in full, its mystery has already left a lasting impact on astronomy. It has inspired public engagement, fueled scientific collaboration, and encouraged imaginative speculation. It has also reminded astronomers that data should be approached with open minds, for not every observation fits neatly into established categories. Sometimes, anomalies are opportunities, opening doors to new discoveries that expand the boundaries of knowledge. Even if no alien structures orbit Tabby's star, the very act of considering such a possibility reflects humanity's curiosity about life beyond Earth. The willingness to entertain extraordinary explanations, while still pursuing evidence-based inquiry, demonstrates a healthy balance between imagination and science. It shows how the quest to understand the universe blends rigorous analysis with a sense of wonder, both of which are essential for progress. Looking forward, Tabby's star continues to be monitored, with new dips occasionally drawing attention. Each event provides fresh data, testing theories, and refining models. The mystery may eventually be solved in a way that seems obvious in hindsight, as many scientific puzzles are. But until that day, the star holds a unique place as one of the most enigmatic objects ever studied, a blinking beacon of cosmic uncertainty that invites us to keep looking up. In many ways, Tabby's star illustrates the beauty of science as an evolving journey rather than a final destination. The path from bewildering observation to eventual understanding is filled with detours, debates, and discoveries. The star's erratic light curve is like a riddle written in starlight, challenging us to decipher it. Whether its secret lies in dust, debris, or something yet unimagined, the pursuit itself enriches our understanding of the cosmos. Ultimately, Tabby's star serves as a reminder of our small place in the universe. A distant point of light, invisible to the naked eye, has nevertheless captivated human minds across the planet. Its strange behavior has connected scientists, citizens, and dreamers alike in a shared quest for answers. And in that sense, the star's greatest gift may not be the solution to its mystery, but the way it brings people together in awe and curiosity. The star's blinking may someday be reduced to simple astrophysics, a quirk of dust and debris explained in clear terms. But even then, the memory of the mystery will endure. For years, it has stirred imaginations, challenged assumptions, and reminded us that even familiar stars can harbor secrets. In the end, Tabby's star will always be more than a point of light. It will be a symbol of the unknown, the strange, and the endlessly fascinating universe we inhabit. Magnetars are among the most exotic and extreme objects in the universe, known for their unimaginably powerful magnetic fields. These stellar remnants are a type of neutron star, formed when massive stars explode in supernovae and collapse under their own gravity. What makes magnetars different from ordinary neutron stars is the intensity of their magnetic fields, which can be 1,000 times stronger. To put this into perspective, the strongest magnets humans can create in laboratories pale into insignificance compared to magnetars, whose magnetic grip can distort atomic structures themselves. When a star massive enough reaches the end of its life, it can no longer sustain nuclear fusion in its core. Gravity overwhelms the outward pressure of fusion reactions, leading to a collapse so violent that electrons and protons are crushed into neutrons, forming a neutron star. Sometimes, this collapse results in a neutron star with exceptionally rapid rotation and a dynamo effect that generates magnetic fields of incomprehensible strength. When the magnetic intensity reaches around 10 to the power of 1 to 10 to the power of 1 Gauss, the star earns the title of a magnetar, a cosmic behemoth defined by magnetism. The human mind struggles to grasp such numbers. Earth's magnetic field, the one that guides compasses and shields us from solar winds, measures less than 1 Gauss. Even the strongest laboratory fields we can generate reach only a few 100,000 Gauss at best. Ordinary neutron stars already possess magnetic fields in the trillions of Gauss, but magnetars take this to extremes. Their fields are so strong that they can warp space near them, alter physical laws in subtle ways, and potentially pull matter apart at the atomic level. The surface of a magnetar is a realm of chaos and violence. Their crusts are thought to be incredibly hard, yet under the strain of the immense magnetic fields, even such rigidity can give way. When the magnetic field twists and shifts, the crust can crack catastrophically in what are called starquakes. These events unleash colossal amounts of energy, often in the form of high-energy X-rays and gamma rays. A single burst from a magnetar can outshine an entire galaxy for a brief moment, a staggering testament to the forces at play. Astronomers first suspected magnetars existed when they observed mysterious bursts of gamma rays that could not be explained by known cosmic sources. In 1979, a particularly intense event reached Earth's detectors, saturating instruments and briefly bathing our planet in radiation from across the galaxy. Over time, more of these soft gamma repeaters and anomalous X-ray pulsars were discovered, all of which shared unusual behaviors that eventually pointed toward the magnetar model. It became clear that only hypermagnetized neutron stars could account for such phenomena. The magnetic field of a magnetar is not only immensely strong but also unstable. It can rearrange itself violently, similar to how magnetic storms erupt on the sun but magnified to a cosmic scale. When the magnetic field lines reconnect or snap, the energy released is astronomical. These outbursts are so intense that if a magnetar were located within a few dozen light-years of Earth, its radiation could potentially harm our biosphere. Fortunately, the known magnetars are safely distant, many thousands of light-years away. One of the most striking effects of such strong magnetism is its ability to distort matter itself. Normally, atoms have their electrons orbiting in relatively neat, spherical shells. But in the crushing grip of a magnetar's field, electrons are forced into elongated paths, stretching atoms into thin, cylindrical shapes. In essence, matter near a magnetar does not behave as matter does anywhere else in the universe. This strange physics gives scientists rare opportunities to study how fundamental forces act under extreme conditions. Despite their terrifying power, magnetars are relatively short-lived in astronomical terms. Their magnetic fields decay over tens of thousands of years, which is rapid compared to the millions or billions of years that ordinary stars and neutron stars can persist. This means magnetars represent a fleeting but dramatic stage in stellar evolution. As their fields weaken, They may transition into more conventional neutron stars, their brief era of magnetic dominance leaving behind lingering mysteries in the cosmos. The immense magnetic energy trapped inside a magnetar also influences its rotation. Most neutron stars rotate rapidly, some spinning hundreds of times per second. Magnetars, however, often spin more slowly, completing one rotation in seconds rather than milliseconds. This sluggishness is thought to arise because their magnetic fields act as cosmic brakes, dissipating rotational energy quickly. Thus, the very force that defines them also limits their speed, making them unique among their stellar cousins. Magnetars also play an intriguing role in astrophysical mysteries such as fast radio bursts, FRBs. These millisecond-long bursts of radio energy, originating from distant galaxies, puzzled astronomers for years. Recently, evidence has emerged linking at least some FRBs to magnetar activity, specifically to their violent magnetic reconnect ions and starquakes. If magnetars are indeed behind these enigmatic signals, they would provide a partial answer to one of the great questions of modern astronomy, connecting seemingly unrelated cosmic events. Studying magnetars is no simple task, as they are rare and difficult to observe directly. Only a few dozen candidates have been identified in our Milky Way, out of the hundreds of billions of stars that populate it. Their rarity reflects the narrow conditions needed for their creation. Only certain massive stars, under the right collapse circumstances, give rise to magnetars. Yet these few examples have already reshaped our understanding of what neutron stars can become and the variety of behaviors they can exhibit. The radiation from magnetars can be so intense that it challenges our instruments. Detectors meant to capture gamma rays and X-rays can become saturated during bursts, leaving scientists scrambling to interpret data. This overwhelming brightness reminds us of the sheer scale of energies at play. When a magnetar erupts, it becomes briefly one of the most luminous objects in the entire observable universe, a beacon of power that can be detected across interstellar distances. The crust of a magnetar, thought to be a crystalline lattice of neutrons and atomic nuclei, endures stresses beyond imagination. When cracks occur, they reverberate like cosmic earthquakes, releasing both light and particles. These starquakes may also emit gravitational waves, ripples in spacetime itself, though detecting such emissions remains an ongoing challenge for observatories like LIGO and Virgo. If confirmed, magnetar quakes would provide not only electromagnetic fireworks but also vibrational echoes in the fabric of reality. The very existence of magnetars challenges human intuition about stability. How can something so unstable persist at all? Yet nature finds ways to balance forces, even at extremes. For a time, the magnetic tension is held in check by the dense neutron star crust and core. Eventually, though, equilibrium breaks, and violent rearrangements occur. This delicate dance between order and chaos defines magnetars, making them both dangerous and fascinating to study. One of the most famous magnetar events occurred in December 2004, when a giant flare from SGR 1806-20 released as much energy in a tenth of a second as the Sun emits in 150,000 years. Even though it was tens of thousands of light-years away, the burst briefly altered Earth's ionosphere, showing the extraordinary reach of such eruptions. If it had been closer, its effects might have been catastrophic for our planet. This event underscored the raw destructive potential locked within magnetars. Astronomers continue to debate how magnetars fit into the broader family of neutron stars. Some theories suggest all neutron stars may briefly pass through a magnetar-like phase, their fields decaying quickly and leaving little evidence behind. Others argue that only certain progenitor stars, perhaps those with high spin rates or particular chemical compositions, can give birth to true magnetars. Answering this requires more observations and theoretical models, pushing the boundaries of stellar evolution research. Magnetars also serve as natural laboratories for testing physics in regimes unreachable on Earth. Their immense densities, rivaling atomic nuclei, combined with magnetic fields billions of times stronger than anything we can create, provide extreme conditions for studying matter. By observing their emissions and comparing them to predictions, physicists can probe quantum electrodynamics, nuclear interactions, and magnetohydrodynamics in ways impossible in terrestrial experiments. They are, in essence, cosmic particle accelerators and laboratories rolled into one. The light curves of magnetars, how their brightness changes over time, offer crucial clues to their inner workings. Some show steady pulsations, while others erupt with unpredictable bursts. This duality mirrors their internal complexity, with stable rotation punctuated by chaotic magnetic events. By carefully analyzing these patterns, astronomers attempt to decode the processes hidden beneath their surfaces, much like seismologists interpret earthquakes to learn about Earth's interior. Though they are relatively few, magnetars could play significant roles in shaping galactic environments. Their eruptions inject high-energy particles and radiation into surrounding space, influencing nearby gas clouds and potentially triggering or disrupting star formation. On larger scales, they contribute to the energetic ecology of galaxies, ensuring that stellar deaths are not quiet endings but ongoing forces that sculpt the cosmos around them. Magnetars remind us that even stellar remnants can shape the universe long after their parent stars perish. Some magnetars also exhibit unusual radio emissions, blurring the line between them and traditional pulsars. While pulsars emit steady, clock-like radio pulses, magnetars occasionally surprise astronomers with bursts of radioactivity. This crossover behavior suggests a continuum of neutron star states, where magnetars and pulsars are not entirely separate species but points along a spectrum. Each discovery forces scientists to refine classifications and rethink assumptions about how neutron stars behave. Magnetars also challenge technological limits in detection. Their bursts often occur unpredictably, leaving astronomers dependent on wide-field instruments that can catch transient events. Space-based observatories like SWIFT, FEMI, and XMM Newton have been crucial in identifying and tracking magnetar activity. Coordinated observations across multiple wavelengths, radio, optical, X-ray, gamma, allow researchers to build a fuller picture of these enigmatic giants, revealing how different forms of radiation emerge from their violent processes. There is also growing speculation that magnetars may be linked to some of the brightest cosmic explosions ever observed, gamma-ray bursts. Specifically, short-duration bursts may be powered by the birth of new magnetars, their rapid rotation and magnetic fields unleashing torrents of energy in the moments after formation. If this connection holds, it ties magnetars not only to steady outbursts but also to some of the universe's most spectacular and cataclysmic events, expanding their significance even further. In popular imagination, magnetars often take on a role akin to cosmic monsters, their invisible claws stretching across space. Yet they are also symbols of the extreme creativity of nature, showing how diverse the outcomes of stellar death can be. From black holes to neutron stars to magnetars, each remnant tells a different story about the balance of gravity, pressure, and magnetic fields. Magnetars, with their blazing bursts and warped physics, embody the wildest possibilities among these remnants. The study of magnetars remains young, with many open questions still waiting for answers. Why do some neutron stars become magnetars while others remain ordinary? How exactly do their fields decay, and what physical processes drive their starquakes? Can their outbursts be predicted, or are they inherently chaotic? These mysteries ensure that magnetars will remain a frontier of astrophysics for decades, luring scientists deeper into the study of extreme stellar remnants. For humanity, magnetars are safely distant curiosities, yet their existence reminds us of the violent forces lurking in the universe. Though far away, They are a testament to both the fragility and resilience of matter under cosmic pressure. If we could approach one, we would not survive its radiation or magnetism, yet from afar, we can admire the spectacle it provides. The universe hides monsters, but it also gives us the means to study them without falling victim to their power. Ultimately, magnetars embody the paradox of beauty and danger in the cosmos. Their bursts light up the universe, dazzling in intensity, yet they also reveal destruction on scales that humble human comprehension. In studying them, we gain not only knowledge of stellar physics but also a deeper appreciation of the cosmos's extremes. Magnetars remind us that even in death, stars can roar with unparalleled power, leaving behind legacies written in bursts of light and storms of magnetism. The discovery of planets orbiting pulsars came as a shock to astronomers, because pulsars themselves are the remnants of stars that have undergone catastrophic supernova explosions. When such massive stars die, they collapse into neutron stars, objects so dense that a teaspoon of their matter would weigh billions of tons. Pulsars, a subclass of neutron stars, emit beams of radiation that sweep across the cosmos like celestial lighthouses. The environment around them is harsh, bathed in radiation and riddled with extreme gravity, making it seem like the least likely place to find planets. In 1992, however, the unexpected was confirmed. Astronomers Alexander Wolszczyn and Dale Frail detected variations in the timing of pulses from a pulsar named PSRB 1257+12. Pulsars rotate with extraordinary precision, and their beams of radio waves arrive at Earth like clockwork. Small deviations in this timing suggested gravitational influences from orbiting bodies. After careful analysis, the scientists concluded that the pulsar was indeed orbited by at least 2 planets, marking the first confirmed discovery of exoplanets outside our solar system. This discovery was revolutionary because it overturned the assumption that planetary systems only formed around normal, main-sequence stars. Until then, astronomers had expected planets to form in the quiet circumstellar disks of young stars, not in the aftermath of cosmic explosions. Yet here were planets circling a stellar corpse, proving that nature could assemble worlds in environments once thought utterly hostile. It forced scientists to reconsider how planets form and survive in the universe's most extreme conditions. The planets around PSRB 1257+12, sometimes nicknamed the pulsar planets, are roughly Earth-sized. They orbit at distances comparable to the inner planets of our solar system, completing their revolutions in just a few weeks or months. Despite their size, however, they are not friendly places. The radiation pouring from the pulsar would strip atmospheres away and bombard any surface with lethal energy. They are barren, irradiated rocks, enduring a life orbiting a beacon of death rather than a nurturing star. The formation of such pulsar planets is still a subject of debate. One idea is that they are survivors from the original planetary system of the star that went supernova. Somehow, these planets managed to endure the Titanic explosion, their orbits destabilized but not destroyed. Another possibility is that they formed afterward, from debris left behind after the supernova. In this scenario, a disk of gas and dust could have coalesced around the pulsar, similar to how planets form around young stars, giving birth to second-generation worlds. A third hypothesis suggests that pulsar planets might arise when a companion star is torn apart by the pulsar's gravity. The shredded remains could settle into a disk, providing raw material for planet formation. This would make pulsar planets not survivors but children of destruction, born from the ruins of stellar cannibalism. Each possibility underscores the creativity of nature in reshaping chaos into new structures, even in the most unlikely settings imaginable. PSRB 1257+12 remains the most famous pulsar with planets, hosting at least 3 confirmed worlds. They have been given informal names, Draga, Poltergeist, and Phobita, after mythological spirits, reflecting their ghostly existence around a dead star. Draga, the innermost planet, is one of the lowest mass exoplanets known, only about twice the mass of our Moon. Poltergeist and Phobita are larger, closer to Earth's mass. Their eerie names capture the strangeness of these worlds, haunting the remnants of a destroyed stellar system. Another pulsar, PSRB 1620-26, boasts a planet nicknamed the Methuselah planet due to its incredible age, around 12.7 billion years, nearly as old as the universe itself. This planet orbits a system consisting of a pulsar and a white dwarf, making it one of the most bizarre planetary arrangements ever observed. Its existence suggests that planets can form early in cosmic history and survive for eons, even through dramatic stellar transformations, defying assumptions about planetary fragility. The environments of pulsar planets are shaped not only by radiation but also by intense gravity. A neutron star packs more mass than the Sun into a sphere barely 20 kilometers across, creating a gravitational field so strong that time itself runs slower near it. For planets orbiting close by, this means enormous tidal forces that could stress and reshape their interiors. Any attempt at habitability would be instantly ruled out by these crushing conditions, yet as scientific curiosities, they remain fascinating. The discovery of pulsar planets also had profound implications for the search for exoplanets in general. They were found not by direct imaging or transit methods, but by analyzing subtle changes in pulsar timing. This demonstrated that planets could be detected through a variety of indirect methods, opening the door to creative approaches in planet hunting. It proved that exoplanets are not limited to familiar solar-type systems but can exist in places humans never dared imagine. Despite their inhospitable conditions, pulsar planets reveal the resilience of planetary formation processes. The fact that planets can either survive or reform in such hostile environments suggests that planet building is a near-universal outcome of cosmic dynamics. Wherever there is material and enough time, nature seems determined to sculpt planets. This realization strengthens the belief that planets are common throughout the galaxy, increasing the likelihood of discovering more Earth-like worlds elsewhere. One particularly striking feature of pulsar planet systems is their stability. Despite orbiting such violent remnants, many pulsar planets maintain relatively stable orbits over long timescales. This stability arises from the precision of pulsar timing measurements, which allow astronomers to chart their motions with incredible accuracy. The fact that these orbits persist suggests that even after chaos, order can emerge, offering profound lessons about resilience in the cosmos. Yet the mystery of how pulsar planets manage to exist at all continues to puzzle researchers. Supernova explosions are so destructive that they should obliterate any nearby planets, either engulfing them or ejecting them into interstellar space. The survival hypothesis struggles against this immense violence, making the idea of second-generation formation more appealing. Still, both possibilities remain viable, and each discovery adds new pieces to the puzzle of planetary endurance. The presence of pulsar planets also raises intriguing questions about potential habitability in extreme conditions. While radiation levels make them uninhabitable for life as we know it, could some exotic forms of life adapt to such environments? While unlikely, this question highlights the importance of not limiting our imagination when considering the possibilities of life in the universe. Nature often defies human expectations, and pulsar planets remind us to keep open minds. From a scientific perspective, pulsar planets provide unique laboratories for testing gravitational theories. The precise timing of pulsar signals allows astronomers to measure planetary masses and orbital dynamics with extraordinary precision. In some cases, these measurements surpass what can be achieved for planets around normal stars. As a result, pulsar planets serve not just as curiosities but as tools for advancing our understanding of planetary systems and the physics of gravity. The eerie, barren landscapes of pulsar planets are easy to imagine, rocky surfaces scorched by relentless radiation, with no atmospheres to shield them. If one could stand on such a world, the pulsar in the sky would dominate the heavens, a small, fierce point of light pulsing rhythmically. Instead of warmth and sunlight, the world would be bathed in deadly beams of energy, its surface lifeless but fascinating in its desolation. These visions capture the stark beauty of worlds circling dead suns. The discovery of pulsar planets also reshaped the narrative of how exoplanets are studied. They were, after all, the first confirmed exoplanets ever detected, preceding even the famous 1995 discovery of a planet orbiting a sun-like star. That such a historic breakthrough came not from a serene, life-friendly system but from the corpse of a star emphasizes how unpredictable science can be. The first chapter of exoplanetary exploration was written in the shadows of stellar death. Since then, the number of known pulsar planets has remained small, with only a handful identified. This rarity could reflect either their true scarcity or the difficulty of detecting them. Pulsar timing requires exceptional precision and long-term monitoring, which limits the number of systems studied in detail. Still, the fact that even a few have been found suggests that many more may exist, waiting to be uncovered by persistent astronomers and more advanced instruments. Pulsar planets also inspire philosophical reflections on resilience and rebirth. Even after the death of a star, even after catastrophic explosions, planets can emerge or survive, circling the ashes of their progenitor. They symbolize continuity in the universe, a reminder that destruction often gives rise to new beginnings. In this sense, pulsar planets embody one of the cosmos's most profound themes: out of chaos, creation persists, often in the least expected places. These planets also demonstrate the importance of interdisciplinary science. Understanding them requires not just astronomy but astrophysics, planetary science, and even geology to imagine their surfaces. The study of pulsar planets forces collaboration between scientists who study stellar deaths and those who study planetary births. This merging of fields enriches both, expanding humanity's collective vision of what planetary systems can be like. As technology advances, future observatories may uncover more pulsar worlds, potentially with greater diversity. Some might be gas giants stripped of their atmospheres, reduced to rocky cores. Others might be icy remnants, circling farther out where radiation is less intense. Each new discovery would add to the catalogue of planetary diversity, showing that the cosmos never stops surprising us with its creative architectures. The uniqueness of pulsar planets also sparks curiosity in science fiction and popular culture. Writers and artists imagine alien civilizations enduring the harshness of such systems, building protective domes or harnessing the pulsar's energy. While purely speculative, these visions capture the imagination and remind us of the role pulsar planets play not just in science but in inspiring human creativity. They are perfect canvases for exploring ideas about survival and adaptation in extreme environments. In a broader cosmic context, pulsar planets are a bridge between death and rebirth. Their existence shows that planetary systems do not end with the destruction of their parent stars. Instead, they can endure or regenerate, carrying on in altered forms. This continuity expands our view of cosmic evolution, demonstrating that planetary life cycles are more complex and resilient than once thought. Pulsar planets are living proof of the universe's ability to recycle its materials into new forms. The timing precision of pulsars also makes them cosmic clocks, and planets around them introduce subtle ticks in these rhythms. By studying these deviations, astronomers not only discover planets but also refine measurements of fundamental physics. In this way, pulsar planets contribute indirectly to experiments probing the very fabric of space-time. They are part of a grander story in which planets are not just passive bystanders but active participants in cosmic measurements. Ultimately, pulsar planets remind us that the universe is stranger and more inventive than human imagination often allows. They circle dead stars, endure unimaginable radiation, and exist in defiance of expectations. Their discovery was not just an astronomical milestone but a philosophical one, forcing us to accept that planets and perhaps life can exist in forms and places beyond our assumptions. They expand the boundaries of what is possible, and in doing so, they expand us. Though lifeless and hostile, pulsar planets are a testament to the indomitable processes of planetary formation. They stand as silent witnesses to stellar death, orbiting steadily while their parent pulsars sweep their beams across space. They are not welcoming, but they are enduring, and that endurance speaks to the underlying tenacity of matter in the cosmos. In their strange orbits, they carry lessons about survival, rebirth, and the endless creativity of the universe. When astronomers first began discovering exoplanets, most expected to find stable worlds orbiting serenely around their host stars, not celestial bodies caught in the act of destruction. Yet among the thousands of exoplanets catalogued, some are literally disintegrating before our eyes. These so-called disintegrating worlds are rocky planets so close to their stars that their surfaces are being vaporized, stripped away grain by grain into streams of dust. The discovery of these doomed planets revealed that not all planetary systems are harmonious havens, some are sites of cosmic ruin. The story of disintegrating planets began with Kepler, NASA's prolific planet-hunting telescope. Kepler detected planets by observing tiny dips in starlight as they crossed in front of their stars. But in certain cases, astronomers noticed dips that looked strange, irregular in shape and varying in depth from transit to transit. Unlike the clean, sharp signal of a solid planet, these signals looked more like the shadow of something fuzzy and ever-changing. The explanation that emerged was astonishing. The planets themselves were trailing clouds of dust as they crumbled apart. One of the first and best-studied examples is KIC 125575448b, discovered in 2012. This small planet, only about the size of Mercury, orbits its star so closely that a year lasts just 15.7 hours. At such an extreme distance, the planet's surface is heated to more than 2000 degrees Celsius, hot enough to vaporize rock. Material escapes from the planet, carried away as dust that forms a comet-like tail. With every orbit, the planet loses more of itself, ensuring that in astronomical terms, it is living on borrowed time. The transit signature of KIC 125575448b is one of the most dramatic in exoplanet science. Instead of repeating with uniform dips, the starlight sometimes dims deeply, sometimes barely at all, depending on how much dust the planet is shedding at the time. This variability betrays the planet's unstable condition. Scientists describe it as watching a world crumble in real time, a cosmic act of erosion happening on a scale that would eventually reduce the planet to nothing more than a dusty memory around its star. Disintegrating worlds challenge our understanding of planetary survival. Most models of planetary systems assume that planets, once formed, remain relatively stable unless perturbed by gravitational interactions. But these systems show that extreme proximity to a star can doom a planet to a short, fiery existence. The very conditions that make these planets easy to detect, their rapid orbits and frequent transits, also ensure that they cannot last forever. They are cosmic mayflies, living fast and dying young on astronomical timescales. Another famous disintegrating world is KOI 2700b, discovered with Kepler data in 2014. Like KIC 125575448b, it shows an asymmetric transit curve, indicating a trailing dust cloud. What makes KOI 2700b particularly interesting is the suggestion that the dust grains vary in composition, perhaps including silicates and metals vaporizing at different temperatures. By studying the color dependence of the dimming, astronomers gain clues about the chemical makeup of these doomed planets, essentially dissecting their rocky bodies from afar. These worlds provide unique laboratories for studying planetary interiors. As material escapes, it carries with it signatures of the planet's composition. On Earth, geologists must drill or infer interior structure from seismic waves, but in disintegrating exoplanets, the star itself acts as the laboratory lamp, backlighting the dust. By analyzing how the dust absorbs and scatters starlight, astronomers can infer what minerals make up the planet's crust and mantle. It is as if the planets, in their death throes, reveal their innermost secrets. The process of disintegration is driven by intense stellar radiation. At such close distances, not only is the surface temperature extreme, but the star's tidal forces also pull at the planet. These tides can crack the surface, allowing gases and particles to escape more easily. Once material escapes the gravitational grip of the planet, it is swept into orbit around the star, forming the dusty tail. The result is a delicate balance between planetary gravity trying to hold itself together and the relentless energy of the star tearing it apart. In some cases, disintegrating worlds may be the stripped cores of once larger planets. Gas giants that migrated too close to their stars might have lost their atmospheres first, leaving behind only dense rocky or metallic cores. These remnants, unable to resist the continued heat and tides, then begin shedding even their solid material. Thus, what astronomers now observe as tiny crumbling rocks may once have been mighty worlds, transformed into shadows of their former grandeur by stellar violence. The existence of these planets raises intriguing questions about planetary lifespans. How long can such a world survive once disintegration begins? Estimates suggest that planets like KIC 125575548b may persist for only tens of millions of years, a blink of an eye compared to the billions of years stars typically live. This brevity makes them rare catches, like seeing a candle in its final flickers. We may only glimpse a few such systems simply because most planets in this state have already been destroyed. From a broader perspective, disintegrating worlds highlight the dynamic, often violent nature of planetary systems. Our solar system, with its relatively stable planets, may give the impression of longevity and order. Yet the universe reveals many examples of instability, destruction, and renewal. Disintegrating planets remind us that not all worlds are blessed with stability. Some are doomed by their very orbits, caught too close to their stellar parents, destined to fall apart under relentless heat. Disintegrating worlds also overlap with another mystery, unusual dips in starlight, such as those once attributed to alien megastructures around Tabby's star. While Tabby's star is not thought to host a disintegrating planet, the concept of dust clouds around stars has become central to interpreting puzzling light curves. The lesson from disintegrating worlds is that not all transits are caused by solid, spherical planets. Sometimes, it is the dust of a dying planet casting shadows, teaching caution in exoplanet interpretation. The physical mechanics of dust production in disintegrating planets is itself a rich area of study. Different minerals vaporize at different temperatures, so the composition of the dust tail may shift depending on stellar activity or the planet's orbital phase. These changes can alter the brightness and shape of the transit curve, making each orbit slightly different from the last. This variability adds complexity but also provides valuable information about planetary geology, effectively allowing astronomers to run a continuous experiment on planetary disintegration. Some researchers speculate that disintegrating planets might seed their stellar environments with dust and metals, potentially enriching surrounding space. Over time, this material could accumulate into new structures, perhaps even contributing to the formation of additional planets or rings around the star. In this sense, a disintegrating world may not simply vanish but may recycle its matter into the wider system, becoming part of the ongoing cosmic cycle of destruction and creation. There is also a haunting beauty in imagining these worlds. If one could somehow stand on the surface of such a planet, the star would loom impossibly large and fierce in the sky, its heat unbearable. The ground itself might crack and hiss as rock sublimates into vapor. A constant wind of particles would stream upward, feeding a dusty plume trailing the planet's orbit. The sky would be filled not with clouds of water, but with clouds of its own disintegrated body, a perpetual storm of self-destruction. The discovery of disintegrating planets further expanded astronomers' catalogue of planetary diversity. Before their detection, no one anticipated that rocky planets could visibly evaporate into dust clouds. Now, they represent one of the many strange categories of exoplanets, alongside hot Jupiters, super-Earths, and ocean worlds. They illustrate the creativity of planetary evolution, showing that nature produces not only thriving, stable planets but also fragile, doomed ones caught in acts of demise. Disintegrating planets also underscore the importance of precision in astronomy. The only reason these worlds were detected is because Kepler and subsequent observatories could measure minuscule changes in starlight. Without such precision, the irregular dips might have been dismissed as noise. Instead, careful analysis revealed the telltale patterns of dust clouds, highlighting how advances in technology open windows to phenomena that would otherwise remain hidden. Interestingly, the same physical processes destroying these planets might also be used to study their atmospheres, if any remain. As dust escapes, it could carry volatile compounds that briefly survive in gaseous form before ionization. Spectroscopic analysis of such materials might one day provide chemical fingerprints of elements and molecules, offering a window into planetary atmospheres that would otherwise be inaccessible. Thus, even as they die, these planets give scientists tools to probe alien chemistry. In terms of cosmic storytelling, disintegrating worlds resonate with themes of impermanence and transformation. They are tragic figures, consumed by the very stars that give them light, yet in their destruction they reveal truths about planetary composition and system dynamics. Their brief existences remind us that the universe is not static but always evolving, with worlds rising, thriving, and eventually falling apart. Even planets, often seen as stable anchors, are transient in the grand sweep of cosmic time. Some disintegrating planets may leave behind nothing but faint dust belts circling their stars. Astronomers speculate that such belts, if observed in other systems, could be the silent graves of once solid worlds. Detecting these remnants could expand our knowledge of how many planets succumb to disintegration. In turn, this would help refine models of planetary lifetimes, migration, and stellar interaction, painting a fuller picture of the fates awaiting worlds in extreme orbits. The study of disintegrating worlds also intersects with the search for habitability. While these planets themselves are uninhabitable, their presence warns astronomers to carefully consider stellar proximity when evaluating exoplanets. Too close, and planets risk destruction; too far, and they may be frozen. In between lies the habitable zone, a delicate balance. Disintegrating worlds mark the boundary of this spectrum, illustrating the dangers of orbits that venture too near to stellar infernos. Over time, more examples of disintegrating worlds may emerge, especially as new observatories like the James Webb Space Telescope and Plato refine transit observations. Webb's ability to analyze spectra in infrared could identify the specific minerals escaping from these planets, turning each into a case study in exogeology. With such tools, the death of these planets will not be in vain, as they enrich our understanding of planetary diversity and the physics of extreme environments. The rarity of catching planets in this state cannot be overstated. Because disintegration happens relatively quickly on cosmic timescales, most planets that begin the process are gone before astronomers can observe them. The fact that we have found even a few examples is remarkable, suggesting that many more must have existed over galactic history. Each one represents a fleeting stage in planetary evolution, like snapshots of worlds caught in the act of vanishing. Disintegrating planets also echo myths of doomed worlds in human imagination. Across cultures, stories of burning, falling, or crumbling lands have been told as allegories of fragility and impermanence. The reality of such worlds in the cosmos gives these myths a new resonance, showing that planetary destruction is not only metaphorical but literal on cosmic scales. The universe itself writes stories of creation and loss, more dramatic than any human tale. The fragility of these planets contrasts sharply with the immense forces that shape them. On the one hand, gravity forged them from cosmic dust billions of years ago. On the other, the relentless heat of their stars now dismantles them. They exist caught between creation and annihilation, embodying the tension that defines much of cosmic evolution. They are both triumphs of planetary formation and victims of orbital fate, existing only as long as the balance holds. Ultimately, disintegrating worlds are reminders of the transient nature of cosmic stability. Even planets are not forever. The orbits that sustain them can betray them, pulling them too close to destructive fires. Yet in their demise, they contribute to science, offering clues about planetary composition, star-planet interactions, and the boundaries of habitability. Their crumbling bodies enrich our knowledge, ensuring that their sacrifice adds to humanity's growing understanding of the cosmos. For astronomers, each disintegrating world is like a message written in dust. Their irregular shadows whisper of minerals, heat, and the inevitability of loss. They are signals from systems on the edge of collapse, warning us of the fragility of planets in certain orbits. Each detection is a bittersweet triumph, the joy of discovery mixed with the melancholy of watching a world die. They are cosmic tragedies, but ones that illuminate the grandeur and peril of planetary existence. In the end, disintegrating planets remind us of the impermanence of all things, even celestial bodies. While Earth seems stable in its orbit, the universe shows us countless other possibilities, some serene, some violent. Planets that crumble before their stars are among the most dramatic examples, teaching us that nothing, not even worlds, is immune to change. Their fading dust trails are the ultimate symbol of transience, fleeting signatures of worlds that once were, now dissolving into the light of their stars. Rogue planets are among the most mysterious and haunting objects in the universe, worlds that drift through the cold emptiness of interstellar space with no parent star to call home. Unlike the planets of our solar system, which are held in stable orbits by the sun's gravity, rogue planets have been cast out of their systems, left to wander in eternal night. They drift without sunlight, without warmth from a nearby star, alone in the void. The very idea challenges the way we define a planet, because without a star, they exist in isolation, unseen except when they betray their presence by rare and subtle clues. Scientists believe rogue planets may be more common than we once thought. Some estimates suggest there could be more rogue planets in the galaxy than stars, an astonishing possibility that reframes our understanding of planetary abundance. If true, it means that for every star we see twinkling in the night sky, there may be multiple planets drifting unseen between them. These worlds are invisible to our eyes, too faint to reflect light, detectable only when they pass in front of background stars or reveal themselves through gravitational microlensing. Gravitational microlensing has become the primary tool for finding these wandering worlds. When a rogue planet drifts in front of a distant star from our perspective, its gravity bends and magnifies the starlight, producing a temporary brightening. The duration of this event tells astronomers something about the planet's mass. Shorter events point to smaller bodies, while longer ones suggest more massive planets. It is an indirect method, but it has given us the first solid evidence that rogue planets exist in staggering numbers. The origins of rogue planets are still debated, but most theories converge on two main pathways. Some are likely ejected from their planetary systems during violent gravitational interactions, flung into space when larger planets destabilize their orbits. Others may have formed alone in interstellar clouds, much like stars, but too small to ignite nuclear fusion. In both scenarios, The result is the same, a world without a sun, wandering endlessly through darkness. What would it be like to stand on the surface of a rogue planet? The scene would be utterly alien. The sky would not be brightened by a star, it would be black and filled only with the faint glimmer of distant galaxies. The temperature would plummet to extremes, with no external source of heat. Yet if the planet retained internal warmth from formation or radioactive decay, beneath its icy crust there might be oceans of liquid water. This has led some scientists to speculate that even these lonely wanderers could harbor life deep within. The possibility of life on rogue planets is one of the most intriguing questions in modern astronomy. Without sunlight, photosynthesis as we know it would be impossible, but life could thrive around geothermal vents, much as it does on Earth's ocean floors. Microbial ecosystems that rely on chemical energy rather than sunlight might persist beneath insulating ice layers. If such life exists, rogue planets could serve as vast, hidden arcs of biology, carrying microbial passengers through interstellar space. Detecting such life, however, is an enormous challenge. Rogue planets are difficult to study even in terms of their basic properties, let alone their potential habitability. Most are too far away to probe directly. But future telescopes with advanced infrared sensitivity, like the James Webb Space Telescope and its successors, may one day capture faint heat signatures from rogue planets. By analyzing that radiation, we could learn about their atmospheres, their compositions, and perhaps even hints of subsurface activity. The sheer number of rogue planets is what makes them so captivating. If the estimates are correct, the Milky Way alone could host trillions of them, meaning they outnumber the stars themselves. This suggests that planetary ejection is a common fate, not a rare accident. Planetary systems may form more worlds than they can keep, with gravity deciding which survive and which are cast out. In this view, rogue planets are not outliers but natural byproducts of cosmic evolution. These planets also raise fascinating questions about interstellar travel and panspermia. Could rogue planets act as vehicles for spreading life between stars? If a planet with microbial life were ejected from its home system, it might wander for billions of years, preserving its biosphere under layers of ice. If it eventually passed near another star, it could deposit comets or fragments carrying biological material, potentially seeding life elsewhere. In this way, rogue planets may be agents of cosmic distribution. The discovery of rogue planets has forced astronomers to rethink the boundaries of planetary systems. Traditionally, planets were defined by their relationship to stars, bound in neat orbits. But rogue planets are independent, existing without stellar companionship. This has sparked debate about whether they should even be called planets or whether a new category is required. Yet the term rogue planet captures their essence, evoking both their isolation and their untamed journeys across the galaxy. Rogue planets can also be massive, rivaling the size of Jupiter or even exceeding it. These giant worlds, when freed from their stars, may resemble failed stars known as brown dwarfs. The line between a large rogue planet and a small brown dwarf is blurry, and both may share similar traits, such as faint infrared glows from residual heat. Observations of these objects blur distinctions in classification, reminding us that nature often refuses to fit neatly into human categories. Smaller rogue planets, perhaps the size of Earth or Mars, are far more difficult to detect. They produce microlensing events so brief and faint that only the most sensitive surveys can catch them. Yet they may be the most numerous, representing countless Earth-sized wanderers roaming unseen. The thought that there could be untold numbers of Earth-mass planets drifting alone is staggering, a silent galaxy of worlds lost to the void. Rogue planets also invite speculation about their moons. If a planet were ejected with a moon still gravitationally bound, the two would wander together through interstellar space. Such a system might provide additional stability, with tidal heating between the planet and moon creating energy that could sustain subsurface oceans. In this scenario, even in the absence of starlight, moons of rogue planets might host dynamic environments capable of supporting life. Culturally, rogue planets have captured imaginations as symbols of solitude and resilience. They feature in science fiction as wandering refuges, hostile wastelands, or secret havens hidden from the galaxy. In stories, they often represent loneliness or independence, mirroring their real-life nature as solitary travelers. Yet they are also powerful reminders of the vastness of space, where entire worlds can drift unnoticed, their stories untold, their surfaces unseen. The study of rogue planets also deepens our appreciation of the fragility of planetary systems. Our solar system appears stable now, but it was once chaotic, with giant planets migrating and smaller bodies scattered. Earth could have been among those ejected had circumstances been different. That realization underscores how precarious planetary survival can be, and how fortunate we are to orbit a life-sustaining star. Rogue planets embody the fates of worlds less lucky. Some scientists wonder if rogue planets could ever be colonized by advanced civilizations. In theory, a technologically advanced society could harness geothermal or nuclear energy on such worlds, constructing habitats beneath the surface or within thick insulating atmospheres. Because rogue planets wander without a fixed orbit, they would be stealthy refuges, hidden from detection. For speculative thinkers, they represent not just lost worlds but possible sanctuaries in the endless dark. The thermal environment of rogue planets is one of their defining features. Deprived of stellar warmth, they radiate away heat over eons. Yet massive planets with thick hydrogen atmospheres might retain enough warmth to support liquid water on their surfaces. Such exotic conditions challenge our ideas of habitability, suggesting that life could exist even without starlight, sustained by the slow release of planetary heat. In this sense, rogue planets expand the cosmic definition of what it means to be habitable. Astronomers continue to refine estimates of rogue planet populations using surveys like OGLE and MOA. Each detection adds to the growing realization that they are common, not rare. Future space missions dedicated to microlensing, such as the Roman Space Telescope, will likely uncover thousands more, mapping their abundance across the galaxy. This emerging census will revolutionize our picture of planetary distribution, revealing how many worlds truly wander alone. The mystery of rogue planets extends to their ages. Some may be as old as the galaxy itself, ejected billions of years ago during its turbulent youth. Others may be recent castaways, flung from young planetary systems still settling into order. Each rogue planet carries a hidden history, shaped by its birth, its violent ejection, and its long solitary voyage. They are archives of planetary evolution, though locked away in darkness, waiting for us to uncover their secrets. Unlike stars, which shine brightly and betray their presence across vast distances, rogue planets are quiet. They emit no light of their own, no obvious signals of their existence. They are the dark matter of the planetary world, invisible until chance aligns them with a background star. This invisibility gives them an aura of mystery, as if the galaxy is filled with ghosts of worlds, unseen companions drifting silently between suns. Despite their loneliness, rogue planets may not always be entirely cut off from the galaxy. As they drift, they pass near stars and stellar systems, occasionally feeling the tug of distant gravity. Some may even be captured into new orbits, becoming part of foreign planetary families. This recycling of worlds suggests that planetary destinies are not fixed. A rogue may wander for eons only to find a new home, reshaping our idea of permanence in cosmic relationships. One of the most profound implications of rogue planets is how they shift our perception of the universe. When we look at the night sky, we see stars as the dominant actors, with planets orbiting invisibly around them. But if rogue planets are more numerous than stars, then the true galaxy is one where planets dominate, even if unseen. The galaxy becomes a realm of dark, drifting worlds, more numerous than the glowing points we admire. Rogue planets also remind us of the violence inherent in planetary systems. Their ejection often comes from gravitational chaos, where giants like Jupiter scatter smaller bodies or destabilize their neighbors. These processes leave behind survivors in orbit and castaways in interstellar space. The quiet beauty of a stable planetary system masks a history of upheaval, where many worlds were sacrificed to forge lasting balance. Rogue planets are the scars of that cosmic struggle. Even in their isolation, rogue planets inspire awe. They embody both loss and resilience, stripped of their stars yet persisting as complete worlds in their own right. Their existence challenges anthropocentric ideas of stability and belonging. In them we see reflections of exile and endurance, of wandering and survival. They are lonely, yes, but also enduring symbols of the universe's capacity to create and sustain worlds in every imaginable context. The search for rogue planets is still in its infancy, and much remains unknown. Each new detection pushes us further toward a deeper understanding of how common they are, how they form, and what secrets they may hide. Whether barren wastelands or hidden havens of life, they expand our vision of what a planet can be. In the silence of interstellar space, they drift as cosmic enigmas, waiting for the day when humanity can explore them directly. In the end, rogue planets stand as powerful symbols of the universe's vastness and unpredictability. They remind us that worlds are not always bound, that the ties to stars can be severed, leaving planets to wander in solitude. Yet in that solitude lies mystery, beauty, and perhaps even the seeds of life. The galaxy may be filled with these lonely wanderers, unseen companions to the stars, whispering of cosmic journeys that stretch far beyond the bounds of light. Hypervelocity stars are some of the most thrilling travelers in the galaxy, racing through space at speeds so extreme that they can break free from the Milky Way's gravitational grip. Unlike most stars, which calmly orbit the galactic center, hypervelocity stars are fugitives, launched by powerful gravitational interactions into intergalactic space. Their existence was first confirmed in the early 2000s, and since then, astronomers have been piecing together the violent events that can hurl stars on such extraordinary journeys. At the heart of many hypervelocity star stories lies the supermassive black hole at the center of the Milky Way. When a binary star system ventures too close to this black hole, one star may be captured while the other is flung outward at incredible speeds. This mechanism, known as the Hill's mechanism, is thought to be the primary way hypervelocity stars are born. It is a cosmic slingshot effect, where gravity tears apart a pair of companions and sends one hurtling away like a stone from a sling. The speeds of these stars are astonishing. Some race along at over 1 million miles per hour, fast enough to eventually escape the galaxy entirely. At such velocities, a hypervelocity star could travel from the galactic center to the edge of the Milky Way in just a few 100 million years, a blink of an eye compared to the galaxy's age. For perspective, our Sun drifts through space at a comparatively leisurely 500,000 miles per hour, yet it remains securely bound to the Milky Way. Hypervelocity stars are rare compared to the billions of ordinary stars, but their discovery is vital for understanding galactic dynamics. Each one carries with it the memory of its violent launch, encoded in its velocity and trajectory. By tracing their paths backward, astronomers can infer where they originated, often pointing toward the galactic core. In this way, hypervelocity stars act like messengers, revealing secrets of the gravitational chaos near the Milky Way's central black hole. But the galactic center is not the only birthplace for hypervelocity stars. Other violent interactions, such as supernova explosions, can also accelerate stars to extreme speeds. In a binary system where one star explodes as a supernova, its companion may suddenly be released from orbit and propelled away at high velocity. Though typically not as fast as those launched by black holes, these runaway stars still travel faster than most, blurring the line between ordinary runaways and true hypervelocity stars. The first confirmed hypervelocity star, discovered in 2005, stunned astronomers. It was moving at more than 850 kilometers per second relative to the galaxy, a speed far beyond what any ordinary process could explain. Its trajectory pointed directly away from the galactic center, lending strong support to the theory of ejection by the supermassive black hole. Since then, dozens more have been detected, each adding weight to the idea that the Milky Way's core is a dangerous, violent place. Hypervelocity stars are not uniform. They can vary widely in size, type, and age. Some are massive, blue-hot stars, bright enough to be seen across great distances, while others are smaller and fainter, harder to detect. The most massive hypervelocity stars burn through their fuel quickly, meaning they may not survive the entirety of their galactic escape. Smaller, long-lived stars, however, could drift between galaxies for billions of years, lonely wanderers of intergalactic space. Observing these stars requires precise measurements of their velocities and directions. Astronomers rely on spectroscopy to detect Doppler shifts in their light, revealing how fast they move toward or away from us. Space telescopes like Gaia have revolutionized this field, mapping the motions of billions of stars with exquisite precision. Thanks to Gaia, astronomers are now uncovering hypervelocity candidates across the sky, painting a more complete picture of their origins and distribution. The existence of hypervelocity stars also has profound implications for the structure of the Milky Way. By studying their trajectories, scientists can test models of the galaxy's gravitational field. The way these stars bend and accelerate under galactic forces reveals information about the distribution of visible and dark matter. In this way, hypervelocity stars become probes of the invisible scaffolding that holds the galaxy together. Imagine what it would be like to witness such a star from a nearby world. A hypervelocity star would streak across the galaxy like a lone traveler, leaving behind its birthplace forever. To inhabitants of a planet orbiting it, the night sky would slowly change in profound ways, as constellations shifted rapidly due to their star's enormous speed. The sky itself would tell a story of exile, as familiar patterns of stars dissolved into new arrangements over only a few lifetimes. The fates of hypervelocity stars are as fascinating as their origins. Some will remain bound to the Milky Way, tracing elongated orbits that eventually return them inward. Others will escape completely, crossing the galactic boundary and drifting into the intergalactic void. Once free, they will shine in solitude, perhaps for billions of years, as faint, isolated beacons in the vast darkness between galaxies. Their journeys are among the longest and loneliest any star can undertake. Hypervelocity stars may also carry planetary systems with them. If a star hosting planets is flung outward, some of its planets could remain gravitationally bound, traveling together into intergalactic space. Such planetary refugees would face extreme isolation, cut off from the galactic community, but they might survive nonetheless. In this way, hypervelocity stars may not only scatter starlight across the void but also worlds, potentially carrying life into new realms of the universe. The study of hypervelocity stars also provides insight into the behavior of supermassive black holes. By measuring the number and properties of stars ejected from the galactic center, astronomers can infer the strength of gravitational interactions there. This offers indirect evidence of how stars and stellar systems behave near such an extreme environment. Hypervelocity stars are like breadcrumbs leading back to the black hole, offering clues about processes too distant and violent to observe directly. One of the most intriguing aspects of hypervelocity stars is the sheer energy required to launch them. To accelerate a star with many times the Sun's mass to galactic escape velocity demands unimaginable gravitational forces. This highlights the incredible power of supermassive black holes, which can bend, capture, or fling entire suns as easily as pebbles. The very existence of hypervelocity stars is a testament to the raw energy lurking at galactic centers. These stars may also serve as tracers of galactic history. By analyzing their ages and metallicities, astronomers can compare them to the populations of stars in the regions they left behind. This provides a way to study star formation in the galactic center, a region otherwise difficult to observe due to dust and distance. Hypervelocity stars thus become moving fossils, carrying information about environments that are otherwise obscured from view. Hypervelocity stars also raise intriguing possibilities for future interstellar exploration. If humanity ever achieves the technology to hitch a ride on one, it could theoretically serve as a vehicle for crossing intergalactic distances. Of course, the timescales are daunting, millions of years to traverse the space between galaxies, but the thought experiment underscores just how extraordinary these stars are as natural cosmic travelers. They embody the very concept of journey. Some hypervelocity stars may even interact with other galaxies. A star ejected from the Milky Way could, in principle, drift into the gravitational influence of a neighboring galaxy like Andromeda. If captured, it would become part of a new galactic family, an adopted star with a dramatic past. These cross-galactic wanderers remind us that galaxies themselves are not isolated but part of larger cosmic networks where matter and stars exchange hands over eons. Detection of hypervelocity stars is still limited, and many more likely remain hidden. The Gaia mission, however, is changing this rapidly. By providing accurate positions and motions for billions of stars, it has revealed candidates that once seemed indistinguishable from ordinary stars. The next few years may see the catalogue of hypervelocity stars expand dramatically, allowing scientists to test theories of their origin with greater precision than ever before. From a philosophical perspective, hypervelocity stars resonate with themes of exile and freedom. They are stars torn from their homes, separated from their stellar siblings, yet also unbound, moving in directions few others can follow. Their paths through the galaxy are lonely but also independent, making them both tragic and inspiring. They embody the paradox of being cast out yet becoming free, cosmic exiles blazing trails through the dark. The discovery of hypervelocity stars has also inspired artists and storytellers. They appear in speculative fiction as wandering suns, guiding ships across the void or harboring exiled civilizations. In such tales, they symbolize resilience, survival, and the refusal to remain bound by ordinary limits. Their real-life counterparts may be rarer and lonelier, but they no less stir the imagination, offering images of stars tearing across the cosmic sea. Hypervelocity stars also highlight the delicate balance that governs binary systems. A pair of stars orbiting each other may seem stable, but the gravitational pull of a black hole can unravel that bond in an instant. The captured star falls inward to its doom, while the other is thrown outward to freedom. This dynamic shows how relationships in the cosmos, like those among people, can be abruptly severed by forces beyond their control, leading to separation and change. Though hypervelocity stars were only identified recently, they likely have existed since galaxies first formed. The early universe was even more chaotic, with galaxies colliding and black holes growing rapidly. During those times, the ejection of stars may have been more common, filling intergalactic space with exiles. If so, the void between galaxies may be sprinkled with faint, ancient suns, glowing reminders of a more turbulent cosmic youth. The study of hypervelocity stars also informs our understanding of dark matter. Because these stars travel to the edges of the galaxy and beyond, their paths are influenced by the unseen mass surrounding the Milky Way. By tracking them, astronomers can map the distribution of dark matter, testing competing theories about its structure. In this way, Hypervelocity stars are not just curiosities but vital tools for probing one of the deepest mysteries of modern physics. For planetary scientists, the possibility of planets around hypervelocity stars opens new questions. Could such planets survive the violent ejection process? If so, what would life be like on a world careening through the galaxy at breakneck speed? Its night sky would change rapidly, its stellar neighborhood in constant flux. Such environments stretch the imagination, offering a glimpse of possibilities far stranger than anything in our solar system. The ultimate fate of hypervelocity stars is often to wander alone. Once free of their galaxies, they drift endlessly, their light slowly dimming as they exhaust their fuel. They will become white dwarfs, then fade further into black dwarfs, cold embers adrift in intergalactic space. Their journeys, begun in violence, end in silence, but their existence testifies to the extremes of gravitational power and the resilience of matter against even the fiercest forces. In the grand cosmic tapestry, hypervelocity stars are threads pulled loose, racing across the fabric while most remain woven tightly together. Their rarity makes them special, but their significance lies in what they reveal: the power of black holes, the structure of galaxies, and the fragility of stellar bonds. They are outliers, but outliers often tell the richest stories, offering glimpses of processes otherwise hidden from ordinary view. Hypervelocity stars remind us that even stars, which seem eternal and steadfast in the night sky, can be uprooted and set adrift. Nothing in the cosmos is immune to change or disruption. Their furious speeds and lonely voyages are not just astronomical curiosities but symbols of the dynamic, ever-shifting universe we inhabit. They embody the drama of cosmic interactions, where even the mightiest suns can become wanderers, cast across the galaxy by forces too vast to resist. The CMB cold spot is one of the strangest features ever discovered in the relic radiation that fills the universe. The cosmic microwave background, or CMB, is the faint afterglow left behind from the Big Bang nearly 13.8 billion years ago. Across the sky, this ancient light appears almost uniform, with only tiny temperature variations that reveal the seeds of galaxies and cosmic structure. Yet, in 2004, astronomers studying data from the Wilkinson Microwave Anisotropy Probe found something unexpected: a massive region in the southern hemisphere of the sky that was unusually cold compared to its surroundings. This cold region stood out because it was not just slightly cooler, but dramatically so. While typical CMB fluctuations are on the order of millionths of a degree, the cold spot stretches across a vast region roughly 5 degrees in angular size, much larger than most other anomalies, and dips below the average temperature by a significant margin. Its sheer size and depth made scientists question whether it was simply a random statistical fluctuation, or evidence of something far more exotic happening in the early universe. The cold spot is located in the constellation Eridanus, a river-like shape of stars in the southern sky. If you could look at the CMB map projected over the entire celestial sphere, this region would stand out as an oddly cool blemish in an otherwise fairly smooth cosmic quilt. To the human eye, of course, the CMB is invisible, but to microwave-sensitive instruments like WMAP and the later Planck satellite, the cold spot became one of the most prominent mysteries. One early idea to explain the cold spot was the so-called integrated Sachs-Wolf effect. This effect occurs when CMB photons pass through large cosmic voids, regions of the universe with relatively little matter. As the photons cross these underdense areas, they lose energy and emerge slightly cooler. Astronomers wondered if the cold spot was caused by a massive void billions of light-years away, draining the energy of the photons we now detect. Indeed, surveys of galaxies in the direction of the cold spot have suggested the presence of an unusually large cosmic void, sometimes called the supervoid. This underdense region appears to extend for hundreds of millions of light-years, one of the largest known structures in the universe. If real, it could partially explain why the cold spot appears as it does. However, calculations show that even a void of this magnitude might not be sufficient to account for the full depth and scale of the anomaly. This has led some scientists to propose more radical explanations. One idea is that the cold spot could be evidence of a multiverse, a collision between our universe and another bubble universe in the early stages of cosmic inflation. If another universe brushed against ours, it could have left a scar in the CMB, manifesting as an unusual patch like the cold spot. While speculative, the possibility is tantalizing because it links a specific observation to one of the boldest ideas in cosmology. The cold spot also challenges our assumptions about randomness. In theory, the temperature variations in the CMB should follow a Gaussian distribution, with hot and cold regions evenly distributed in a predictable pattern. The cold spot, however, appears statistically unlikely under this framework, making it a potential outlier that hints at physics beyond the standard cosmological model. The debate is ongoing. Is it truly anomalous, or just an extreme but natural fluctuation? Observations from the Planck satellite, launched by the European Space Agency in 2009, confirmed the existence of the cold spot with even greater precision. Planck's measurements of the CMB are more detailed than WMAP's, and yet the cold spot remained in the data. This strengthened the case that it is not simply an artifact of measurement error, but a real and persistent feature of the universe's oldest light. Its confirmation cemented the cold spot as one of modern cosmology's most enduring puzzles. Some researchers argue that the cold spot is not so unusual after all. In their view, the probability of such an extreme region occurring naturally is low but not impossible, much like rolling an unlikely sequence of dice. Others counter that its statistical unlikelihood is great enough to warrant deeper investigation into new physics. This tension highlights the challenges of interpreting cosmic data, where unique, large-scale features can easily be mistaken for signs of deeper truths. The idea of a multiverse explanation has captured public imagination, but it remains scientifically controversial. Inflationary theory predicts the possibility of many bubble universes forming in the early cosmic expansion, but direct evidence is elusive. If the cold spot were truly a sign of a universe collision, it would provide a rare observational window into realities beyond our own. Still, most cosmologists remain cautious, emphasizing that extraordinary claims require extraordinary evidence. Regardless of its origin, the cold spot serves as a reminder that the universe is not always as uniform as we assume. Its sheer scale, hundreds of times larger than our galaxy, makes it difficult to dismiss. Even if it is simply a void, the fact that such a structure exists at all pushes the boundaries of our understanding of cosmic evolution and large-scale structure formation. It is as if the universe itself carries hidden scars from events we barely comprehend. For many, the cold spot embodies the beauty of science, a single observation sparking debates that span from ordinary astrophysics to speculative theories of parallel worlds. It shows how anomalies are valuable, not because they always reveal something exotic, but because they force scientists to test assumptions and refine models. Whether the cold spot is a statistical oddity, a void, or a multiverse imprint, its study enriches our grasp of cosmic history. The cold spot is also a challenge for cosmological simulations. Most computer models of the universe, based on our best understanding of physics, do not naturally produce such features with high frequency. This discrepancy suggests either that our models are incomplete or that we live in an unusual universe where rare events happen to align in surprising ways. The cold spot therefore acts as a stress test for theoretical cosmology. Interestingly, some follow-up surveys in the direction of the cold spot have found fewer galaxies than expected. This supports the void hypothesis to some degree, yet the size of the void still seems insufficient to fully account for the temperature dip. It leaves scientists in an uncomfortable position. The observations point to both a plausible explanation and a lingering mismatch with theory, an ambiguity that continues to drive new research. The cold spot is not alone. There are other anomalies in the CMB that puzzle scientists. These include the axis of evil, a strange alignment of large-scale temperature fluctuations, and hemispherical asymmetry in the CMB's distribution. Together, these features raise the possibility that our universe might not be as statistically simple as we thought. The cold spot, however, remains the most visually striking and widely studied of these anomalies. If the cold spot were caused by a bubble universe collision, it would suggest a profound new paradigm for cosmology. It would imply that our universe is just one of many, and that the boundaries between universes can leave observable imprints. Such a discovery would revolutionize science, pushing us closer to answering fundamental questions about why our universe exists the way it does, and whether countless others exist beyond our perception. Critics of the multiverse interpretation often note that it is difficult to test scientifically. Unlike voids or statistical explanations, which can be investigated through galaxy surveys and mathematical models, the multiverse idea lies at the edge of testability. This makes the cold spot a perfect example of the tension between imagination and evidence in modern science. It is both inspiring and frustrating, pointing toward possibilities but withholding certainty. Even with modern instruments, measuring something like the cold spot is incredibly delicate. The signals are faint, buried in noise, and require painstaking calibration. Scientists have spent years refining techniques to ensure that what we see in the data is real and not the result of instrumentation quirks. The fact that multiple satellites and teams have independently verified the cold spot strengthens confidence that it is truly etched into the fabric of the cosmos. The cold spot also reminds us of the power of cosmic microwave background studies in general. From this faint glow, astronomers have learned about the universe's age, composition, and geometry. The fact that such a vast and profound anomaly exists in the CMB shows how even in a nearly uniform universe, surprises remain. The cold spot is not a mere curiosity, it is a signpost that points us toward the limits of our current knowledge. Some researchers speculate that the cold spot might be connected to dark energy, the mysterious force driving cosmic acceleration. If the large void is real, it could be influenced by the way dark energy affects the growth of cosmic structures. While this connection remains speculative, it shows how the cold spot is entangled with some of the deepest mysteries of physics, linking the smallest quantum fluctuations to the largest scales of cosmic expansion. For observers on Earth, the cold spot lies so far beyond our everyday perception that it feels almost abstract. Yet, in a sense, we are directly seeing an imprint from the dawn of time. The photons that carry the signature of the cold spot began their journey nearly 14 billion years ago, passing through vast structures before finally reaching our telescopes. Studying them is like holding a fossil from the beginning of the universe, a fossil that is strangely warped in ways we cannot yet fully explain. The debate over the cold spot illustrates how science advances through tension. Some argue for conventional explanations, others for exotic ones, and still others for the possibility that chance alone created this feature. The clash of interpretations keeps the field dynamic, ensuring that no single explanation is accepted without rigorous scrutiny. The cold spot, then, is more than a patch of cold, it is a stage where ideas compete, sharpen, and evolve. Looking to the future, astronomers hope to probe the cold spot with even more detailed galaxy surveys. Mapping the distribution of galaxies, voids, and clusters in its direction will help clarify whether the supervoid explanation is sufficient. At the same time, cosmologists continue to refine theoretical models, testing how rare a feature like the cold spot truly is under known physics. Each new observation brings us closer to untangling this cosmic riddle. In popular culture, the cold spot has inspired comparisons to scars, shadows, and even cosmic bruises. It invites the imagination to picture our universe as a bubble floating among others, colliding and jostling in the vastness of a multiverse sea. While these images are poetic, they also capture the profound sense of mystery the cold spot evokes. It is not merely a statistical detail, it feels like a story written in the fabric of space itself. Whether the cold spot is a gateway to new physics or simply an unusual but natural feature, its significance cannot be overstated. It teaches humility, reminding us that the universe often defies expectations. It teaches patience, since resolving its mystery may take decades of careful work. And it teaches imagination, since grappling with its implications forces us to think beyond the comfortable boundaries of our models. If the cold spot is indeed a void, then it tells us that cosmic structure can be more extreme than we once believed. If it is evidence of a multiverse, it tells us that our universe is but one among countless others. If it is chance, it tells us that even in a cosmos ruled by probabilities, extraordinary outcomes are possible. No matter the outcome, the cold spot is valuable because it stretches the scope of our inquiry. Even now, 2 decades after its discovery, the cold spot continues to spark new research papers, debates, and theories. It remains a reminder that despite all our progress in cosmology, the universe still guards its secrets. The cold spot is like a puzzle piece that does not quite fit into the grand picture, urging us to reconsider what we think we know. That enduring mystery is what makes it one of the most captivating features in all of cosmic science. In the end, the CMB cold spot is a testament to the richness of the universe's story. From the faint afterglow of the Big Bang, we detect not only the smoothness of cosmic beginnings but also anomalies that hint at hidden chapters. Whether it proves to be a statistical fluke, a colossal void, or a scar from another universe, it stands as a symbol of how much remains to be discovered. It whispers from the edge of time, urging us to keep looking deeper, questioning harder, and imagining bolder.